Okay, so in this video we're just going to do a little bit of background information so that we can jump into polar area. And so the first thing we're going to do is review area of a sector. And by sector, I simply mean like a slice of a circle, a pizza slice, basically. So if you remember back when you were in pre-calculus, right, if we were trying to find the area of just a slice of a circle of some angle theta, we would take the area of a circle as we know it, pi r squared, and we would find the portion of the circle we wanted in our sector and take that portion of our area. So some theta out of 360 degrees would then be the ratio of the pi r squared that we wanted specifically. Okay, that would give us just this area of this particular slice. Now, the thing is, in calculus, we typically are working in radians, so we'll be using 2 pi, and when we simplify this, the pi's go away, and you simply get an area formula of 1/2 theta r squared. Okay, so that's the first thing I want to remind you of before we really get going here and talk about polar area. Now with polar area, we're usually looking at some sort of course, polar graph, usually curvy. And essentially what we're going to do is we're going to take some section. So let's say we have, I don't know, I'm just going to draw a squiggly line, some sort of curve. And I want to find the area of this particular slice here. Okay. So the difference with polar area from what we're used to with rectangular graphs is that we were normally looking for the area under a curve, so to speak, or between two curves. In this case, it's not so much an area underneath or side to side. It's just in general what's enclosed between them. So it's a much harder thing to describe. So basically, the formula for polar area is different from all of our previous area formulas because it's not based on these rectangles, and instead it uses still an infinite number of slices, but these slices are coming out from the center, right? So we're taking tinier and tinier slices in I guess like a radial pattern almost, coming out from the pole. So it's still doing the concept we used for our initial ideas with integration of taking lots of tiny slices, but its orientation is much different. Okay? Basically, we're finding an infinite number of these sectors here, and we're simply making them smaller and smaller and smaller and smaller and smaller, and so on. And so what it's changing with respect to this time is not a dx or a dy, of course, because we're not talking about x and y anymore, but is in terms of theta. Okay, so I cleared this out so I could draw a little bit better for you, but basically we're taking an infinite number of slices that change with respect to our theta, right, between some theta alpha and some theta beta. That rhymed. And we're adding up these tiny slices here as we go, with each change in theta between these two bounds. So you know where we're going with this. So basically for polar area, it's going to build off of our area of a circle. It's still going to have everything that you see here, right? The difference is simply that we'll pull the 1/2 out front. Our theta is not necessarily a set thing. That's what we integrate with respect to of r squared, right? So we're looking at our radius equation and we're seeing how it's changing with respect to theta. And so that's going from alpha to beta in terms of theta. And this is how you find the area of a polar curve. So you will need to know this formula going into our next examples.